Hello everyone, my name is Jelena Tomic and I'm here with my dear colleague Ivana Jovovic. Say hello please. And together the two of us are going to share our experience in time series forecasting and anomaly detection and all this related to the field of telecommunication. But at the very beginning, I would like to give you some really brief overview regarding data in order to be able after that to highlight what are opportunities and what are on the other side limitations regarding ML application in telco industry. Of course, I'm going to present from the perspective of working for A1 Group. I suppose that all of you already know that it is telecommunication provider, but maybe not all of you know that it is operating in 7 European countries, shown on map, and also it is serving around 29 million customers. So if I give you this information, and if I also say that we are collecting data about customer interactions, that we are collecting data about all our radio networks, then it can be easily concluded that telco is generating a large amount of data, and it is generating data continuously. But let me give you some numbers. For example, per each radio cell within the network, we are collecting around 3,000 KPIs per hour. We have between 3 and 60,000 cells per country and also per technology, from 2G to 5G. Additionally, we are collecting around 150 KPIs per each call within our network. So obviously, we are facing a lot of challenges. So from data perspective, the first challenge would be to ensure accurate and consistent data collection while ensuring data quality. It is also challenging when we have this kind of high dimensional data and high data velocity. From data science side, well, nothing is straightforward, of course, and nothing is like in the books. The first challenge would be to understand all this data. After that, the challenge is to understand the use case on which we are working with all its requirements and with its all limitations. The challenge is to select appropriate statistical approach or ML tool which would be adequate considering data characteristics and also considering the use case goals which we want to achieve. And finally, the challenge is wanted accuracy. But now from ML engineering perspective, we are talking about time complexity, we're talking about computational complexity. Since I mentioned we have this high dimensional data, we are talking about scalability. Since when we are developing some new approach, we want to apply and deploy this approach for 7 different markets. And on top of all of this, there is question of deployment, maintenance, continuous monitoring, and evaluation. But fortunately, there is no room for despair. Telco data shows some really predictable patterns. For example, there is always some long-term increasing or decreasing trend. And as you can see in this upper figure, we have this long-term increasing trend in traffic volume. If we zoom a little bit, often we will observe some daily or weekly seasonality. And this is also expected because if we look some specific cell, we will detect some period of the day during which we can observe peak network usage. And for example, for some residential area cell, this would be during some evening hours, as this is given in the below figure. So we have trend, we have seasonalities, and what to do now? So fortunately, time series analysis tools are designed in such a way to detect trends, to detect seasonality, to detect patterns. So there is a pool of ML approaches which are, at least on paper, ideal to understand telco data, and even further, ideal to forecast this data. So all ML models are equal, but some models are more equal than others. Here you can see some subset of ML approaches which we often use in the process of time series analysis in telco data. So, for example, if we have several time series, if these time series have trend, one type of seasonalities, then we will use some statistical approaches such as ARIMA or exponential smoothing. But if we have more complex trends, or more complex patterns, then we are forced to use more advanced ML tools or AI tools. So for example, if we have multiple seasonalities, then profit would be appropriate solution, but on the other side, profit requires that we need to perform time series forecasting for each time series separately. On the other side, extreme gradient boosting regressors show really good results, but it requires heavily feature engineering. And for example, if we want to be in the field of artificial neural networks, then in theory, LSTM would be a perfect solution for these long-term, multivariate, complex dependencies. But as I mentioned, in theory. In practice, this approach shows really poor results in the case that we have these long sequences. And also, as you know, it requires a lot of examples for training. It is computationally really expensive. And on the top of everything, it is often outperformed with more standard approaches. So if you want to stay in this field of artificial neural networks, then maybe NHITS would be a promising solution. So NHITS is state-of-the-art deep learning approach, and it is designed specifically for time series forecasting. And why it shows good results? Because it is capable to decompose time series into main components, such as trend and different types of seasonalities and residuals, and it is modeling each component separately. Additionally, it is pretty fast, and additionally, it requires significantly less computational costs. So we are really excited about this approach, and we try a little bit with experimenting with it. And finally, I would like to share with you one use case on which we are pretty proud, and why we are proud, because it is aligned with the green initiatives. So one of the main goals of A1 energy saving group is to increase energy efficiency by 80% till 2030, and this should be done compared to 2090 year. And how we can reach this goal? Well, significant step towards reaching this goal can be achieved if we apply adaptive power management. And what this means? This means, for example, if we can perform forecast of the capacity utilization within the network for the following period, if we can detect hours of the day during which we can expect low traffic load, then during these hours we can turn off cells. And if we turn off cells, this means that we are reducing energy consumption, we are reducing operational costs, and additionally we are reducing carbon footprint. So around this idea, we created a smart energy saving use case with the main business requirements which are given on this slide. So this means, for example, if we want to have adaptive power management, first of all, we need 2 ML approaches. One ML approach for forecasting capacity utilization, and the other approach for forecasting number of active users. Forecast should be done with 7 days forecast horizon, with hourly granularity, and forecast need to be done on the level of site sector. And what is site sector? Well, in telecommunication, we consider site sector some coverage area which is served by typically 3 cells. So this kind of LTE architecture is pretty convenient for adaptive power management. Why? Because during these hours with low traffic demands, we can turn off 1 or 2 from these 3 cells. So there is no real need to have all 3 cells active all the time. Additionally, due to some differences in the network configuration, in the network performances or patterns among the countries, it is required to train different models for different markets, and also to enable retraining of the model due to dynamic behavior of the network. So we started, of course, with our research, and during initial research phase, we started to use different feature engineering techniques, such as lag-based features, defining time-based features, rolling statistics, etc. We also tried experimenting with different ML or AI approaches, such as LSTM or extreme gradient boosting. When defining regressor approach, we tried to train 1 model. We'd also tried with training 2 different models, one for the working day and the other for the days of the weekend. And we also tried by training 1 model per each weekday. So after the first initial phase, we selected 3 candidate approaches, deployed them in parallel, and evaluate performances during the period of 3 months. So after this 3-month period, as a final solution, we selected extreme gradient boost approach with 2 regressors. And somehow we expected this kind of results. And why these results was different than in the case that we used one regressor? Well, the difference was that we were able to introduce more lag-based features, and that way to reduce the effect of one-time events and also to enable adaptation or faster adaptation to the changes in the network. So after the research phase, 3 applications have been developed. One app for training purposes, since we want occasional retraining, one for the forecast, and third for diagnostics. So training app perform all necessary pre-processing, feature engineering, defining training set or examples which are going to be used in the training process and based on the last 6 weeks of data history. So as the output of the training app, we have 2 ML approaches, one for forecasting capacity utilization and the other for forecasting number of users. What about forecast app? Forecast app runs weekly in order to perform forecasts for the following week by using, of course, pre-trained models. So this forecasting app for each site sector within the network and for each hour in the following week predicts 2 values. One value which corresponds to the utilization of all available capacities considering analyzed site sector, and the other for forecasting expected number of users within analyzed coverage area. And finally, diagnostic app. Well, diagnostic app also runs once a week in order to evaluate predictive capabilities of the model. So it loads forecasted results for the previous 7 days. It also loads actual values on the level of cell. After that, perform aggregation in order to have the values on the site sector level and in order to be able to perform evaluation. And after that, perform evaluation by comparing forecasted values with the actual values on the level of each site sector and also on the level of the whole network. By evaluation or by comparing, I'm considering calculation on some pretty standard statistic metrics such as mean and standard deviation of the error, mean absolute percentage error, correlation, etc. And finally, all these results are integrated into SON application, and this way, by combining forecasted results on one side with domain-specific logic on the other side, we enabled this adaptive power management, and we enable scheduling cells for this power-saving mode. And this way, we are, of course, improving energy efficiency, while on the other hand, preserving network performances, which was our main focus and main goal of our research work. So now I would like to thank you for this part of presentation and for your attention, of course. And I would like to invite my colleague Ivana to share our experience regarding anomaly detection.
Good afternoon, everyone. A lot of people here. As Jelena mentioned, my name is Ivana, and I'm here today to present the second part of our talk that relies on anomaly detection in radio access networks. First thing first, and let's see what is a radio access network, and then we will focus on anomaly detection. A radio access network, or shortly RAN, is an essential part of a mobile cellular network that connects user devices with the core network. There are 4 types of radio access networks, and they go from 2G, GSM, up to 5G NR. Each of it requires maintaining to perform optimal or to be optimal. So this is the place when anomaly detection comes into play and help us to monitor base station, identify unusual patterns, and try to solve it. We are doing it to the robust statistical method, so we will have a lot of math here. And first we will go through our input data and then output data, and then we will see how the core of our anomaly model works. Our input data are as Jelena mentioned, a lot of KPIs, but here we will take only 20 per OPCO and per country and per technology. So we need a method that can manage 4 different technologies and 6 different OPCOs. So KPIs are grouped in percentage KPIs, and they measure success or drop rates, and they are mostly related to accessibility, retainability, or mobility. Then each of percentage KPIs has its own weight KPIs. It helps us to make an impact of the volume of the value of percentage KPI with higher volume of weight KPI. And they are really, really important to us to make some aggregations, and this method is based on different type of aggregations. We can look at them as attempts or as volume-based KPIs that measure load of our traffic data. And finally, some of these KPIs we look only like a volume KPIs to understand the volume, to understand the load of whole our network. And these inputs, with the magic between, makes the outputs. Output data are most anomaly scores grouped in different kind of levels. So we will take each of these percentage KPIs and look at individual anomaly score, but we can group them as accessibility, retainability, or mobility, and then get grouped anomaly scores. They are calculated as group of individual anomaly scores. And finally, we will have overall anomaly score obtained from grouped anomaly scores. Everything will be shown on our last slide, where we will show how it looks on our graphical user interface and how our end users, our radio engineers, can see the results. Let's take a look of the core of our anomaly detection model. A robust method to tailor a vast amount of data. And there are 4 really interesting phases. The first tool is something that we expect. It is exploratory data analysis, help us to understand data structure, to check data distributions, and finally to identify patterns and trends and seasonality. As Jelena said, we have a lot of it. And when we are fine with it, we go to pre-processing to remove what we don't want, to clean the data. There is a lot of cleaning. And then to cut, if something is not good, to clip, input missing hours, and we are then capable to go to our first module, and it is module related to threshold calculations. After that, we will go to our second module, where we do the anomaly score calculations. To do the anomaly score calculations, we need to set thresholds, and we are doing it every 2 months. So we are taking a range of 60 days to train our data, to set threshold, and then it use it for anomaly scores. About thresholds, we have a lot of types of thresholds. The easy one, the one that we will look more closely, is network anomaly threshold, and it is used in any case. But we want to set some cell anomaly thresholds depending on each type of percentage KPI. Are they accessibility, retainability, or volume, or mobility? And then volume we are doing separately. And then for some KPIs with really good seasonality, we will go and do some cell hourly level thresholds. When we have thresholds, we are calculating anomaly scores. Again, we will have a lot of different types of anomaly score calculations on hourly level, on daily level, and finally we will have a frame level of anomaly scores. Again, depending on type of the threshold, it can be network anomaly score or cell anomaly score. And again, is it individual, group, overall? For each of it, we will deal with all these types. So, a lot of calculations. And which type of calculations? Some are really simple. And for network thresholds, we decided to use interquartile range method. Depending, are we working with the KPI that presents success rate or drop rate? We have direction. And direction help us to choose first or second part of our network threshold formula. Where we apply this network threshold formula, where we apply this interquartile range method to the weighted average values for KPIs. During every timestamp of our 60 days range, we are taking into account all KPI values for all cells in the network. And as Jelena mentioned, depending on the network, we can have just 3,000 or 60,000 of cells. And then if they have a value for weighted KPI, we are using weighted average in this sense. And believe it or not, we get really good results with something really simple. But we didn't want to stop there and try to get something a little bit better. And here are cell thresholds. We want to see how our cells behave when we take into account its historical behavior. And here we set the threshold. Here again, we have success rate, drop rate KPIs, pictures, 60 days time range. In blue is the values of our KPI and the thresholds. The green one is related to network threshold. But as you can see, this cell, as all cells in our network, are really good. So its cell threshold can be little upper, and this is this orange line. But if we don't want to calculate it on a daily level, not want to get a line, but to see what is going on in each hour, we will go to hourly level thresholds, cell thresholds, and get something like red dots or something like that. And you can see it on this zoom in view of our first graph. This is for one KPI that is success rate, and for the second one that is drop rate. For volume KPIs, calculations were really complicated. And we had different type of groups. So we have some groups that relates on working day, and the other one that it related to weekend. We did this per cell and did it per hour. So for every hour, we calculated threshold as 10 percentile. At the end, it wasn't so complicated, but choosing the right group, it was something that mostly Jelena paid attention, but I helped a little. And for daily anomaly score, we did it on a daily level. Aggregation here was a really tricky part. And then we reshape it to hourly based using some hourly share calculations. And this is more or less everything that you need to know about our thresholds. Let's see what is going on with our anomaly scores calculations. Now we have a threshold. Here it is, network threshold, horizontal, but you can choose whatever you want, cell. Each of these cell thresholds can be in this formula. And I choose the easiest path to explain this. So we present the network anomaly score, the calculation for it. So if KPI, and this formula is related just to success rate KPI. So if KPI has a value that it is greater or equal to our network threshold, we do not have anomaly. so it will be 0. But if it is not, then this is the formula used for calculation. And this is used only for hourly anomaly scores that we calculated every hour. And KPI is a raw value of KPI related to timestamp and to a cell. If we want to think not about success rate KPIs, but about drop rate KPIs, we will change the denominator with 100 minus network threshold. If we don't want to deal with network thresholds, we want to deal with cell thresholds, we will change this network threshold by cell threshold. If we don't want to deal with hourly anomaly scores, but we want to do daily or frame, we won't take these raw KPIs, but we will deal with aggregated values on daily or frame level. Frame will take 5 days into consideration, and each day will have its own value. The largest value will be for the largest weight will be for the day for the first day, and every day in the sequence will have it less. And if you think that it is the end of our mathematical calculations, you are wrong. We have a lot more. We are doing, again, some weighting. So on our basic network anomaly score or cell anomaly score, we are applying some of linear, square root, or logarithmic approaches to get adjusted anomaly score values. And here are the formulas that we use, basic math here, that we use for these approaches. And on this graph, I can maybe easily explain what is going on there. So if we have completely degraded cells with anomaly scores 100, it never happens, I think, in any OPCO, in any country, with any operator, I think, because it would mean that nothing is working. Then, if the number of attempts, if the weight value for these KPIs is equal, for example, to 100 attempts, it is always more, but to have basic math. And if the maximum number of, or 99th percentile of the attempts for all cells in that network during the time period of 60 days when we train our model is 200, these are our final results. So with linear approach, we will have anomaly score equal to 50. With a square or square root approach, we will have approximately 71. And with logarithmic approach, we will have approximately 87. So we want to measure not only the anomaly scores, but we want to see the impact of the number of attempts or traffic that these paired weighted KPIs have to list it to range cells in our final table. And for the end, just to see how does it look for our end users, for our radio engineers, every hour we get this table. These are our frame scores on network level, cell level, on overall, or per group that I already mentioned. So if we choose one of the cells in this table, we will get a daily series for each cells. And here are presented daily anomaly scores in the range of 90 days. So if we want to see the behavior of these cells during some big period before, we will have it here. And we can choose to present daily anomaly scores in our table for each of these days, because on our Elasticsearch basis, all these informations are saved. There are also hourly anomaly scores, but I think that they are not used as much as these two approaches. And why did I mention the approaches of linear, square root, or logarithmic? Because our radio engineers want to select or to arrange these cells in different ways, so they can do it at the beginning. I am not sure, is it I'm not seeing it for here, but I hope you do, here by choosing the approach. When you click on one cell, you can see where it is on map, and you can gather different informations about the cell. I didn't present it because maybe they are not for public. And more or less, that's it. So to summarize, we have a robust method that can be applied. It is statistical, so it is controllable. It is unsupervised. We can use a lot of data, as we already said. And we can use the same approach for different technologies. This was initially done by Jelena for LTE technology and for Serbia, but we roll out this for all 6 OPSCO and for now for 3 technology. And I think this is the first step of our long journey. And because it is really a great pleasure working with Jelena. Here is, I can see, they are. Here is Emma, also our 3rd member of Anomaly group, data science group of Sara. And we hope that our next step will be root cause analysis. So I think that is more than enough of us, and that we can stop here. If you have any questions, Jelena is here and she will take it. I'm kidding, both of us are here, so shoot.